Now we've got the cone here. Let's just say, for example, that water's going to leak out at 3 cubic centimeters per second. Not per minute. Let's make it per minute. Okay, 3 cubic centimeters per minute is what water's going to be leaking out of this cone at. So if that's the case here, let's find out what is the change in the height or the depth, which is the same thing as the height. What's going to be the change in the depth of this cone? And this cone is going to be 12 inch by 12 inches. It looks like the 12-inch diameter is shorter than the 12-inch height, but again, use your imagination here. So we got 12-inch by 12-inch cone. We're going to be interested in what is the rate of change in the depth of the water of the cone when the depth of the water in the cone is at 8 inches. All right, now, if we go to take the derivative of this problem like it is, we're going to need the product rule because we got two different variables here. And not only do we have two different variables here when we take the derivative, but we would have two unknowns here because we don't know dr dt and we don't know dh dt. dH dt is what we're actually trying to solve for. So the thing about a cone is you can write the radius of a cone in terms of the height of the cone because it stays consistent throughout. The radius of this cone is 6 inches at the top. So the radius of the cone is half of the height of this cone. The radius of this cone is half of the height of the cone. So that's going to be consistent throughout. The radius is going to be 1/2 h. So if I've already got everything in terms of h here, I'm going to treat this volume formula as volume equals 1/3 of pi times h over 2 squared, which is what you were saying, 1/2, times h. And now we got one variable on the right side. So now we don't need the product rule. So volume is going to be equal to square root 2, you get 4, so it's going to be pi over 12 times h cubed. Is there a question about how I came up with that?
Where did h over 2 come from?
The radius is always half of the height in this cone.
Oh, okay.
So that's right in one variable in terms of the other. Any other questions here? All right. So it's derivative time. This is as reduced down as we're going to get it. So dv dt is going to equal to pi over 4 times h squared dh dt. Any question here? All right. Now, what's the height I'm interested in? Or the depth? 8. So it's going to be 64 pi over 4. Right? Now what about my dv dt?
Oh, is that just 3?
All right, we've got to be careful on this one. We've got 3 here, but what's happening in this case that's different from the others? It's getting smaller, right? The balloon, when we blew up the balloon was getting bigger. When we threw the rock in the pond, the area of the ripple was getting bigger. But here, my volume is actually getting smaller, so it's going to be -3. So I got -3 equals to 16 pi dh dt. So -3 over 16 pi equals dH dt. And again, we could leave it like that, or we could get the decimal approximation there. But it should make sense that this is negative, because why? The water level is dropping.